Okay, so what we're going to look at now is the third kind of quadratic equation that I could ask you to graph. This is called intercept form. Specifically, we're looking at x-intercepts now. The reason we can get these x-intercepts so easy is because of the zero product property, and I'll explain that when we do our example. But what we really have to focus on are 2 points to get us started. This slide here is just to try to help us understand a little bit about how this function works. So if we check out the first statement here, it says that our x-intercepts are a result of the x values that we can plug in to make each one of these quantities separately 0. And what that does is it actually forces us to have an output of y being 0. So whatever x makes this quantity 0 forces an output of y being 0. And whatever x makes this quantity 0 also forces y to be 0. So we really do have x-intercepts by doing this. Secondly, the axis of symmetry. If we have two intercepts, they are on opposite sides of the parabola. So if we have two intercepts, what we're able to do is average them to find the line of symmetry, the axis symmetry, smack dab in the middle of our parabola. So that is an easy way this time, I believe, to get the axis symmetry. And we should remember that the axis symmetry helps us get our vertex. Our vertex is always the, I'm going to abbreviate here, the axis symmetry, comma, the y value that you get when you substitute the axis symmetry into the original function. These 4 pieces of information are to help clarify what I've explained in the last 2 videos. Some information about A again tells us about the picture, and if our picture doesn't correlate to what we think it should do, we need to start over again. If A is positive, the parabola will open up. If A is negative, the parabola will open down. Those 2 things kind of go together to get that piece of information. And then the last 2 here say that if A's absolute value is greater than 1, then it's going to be narrower. This is a multiplier in the front, a coefficient in the front that will make it happen, that will make the parabola narrower because it happens faster due to that multiplier at the beginning. And then also, if this A at the beginning is a fraction less than 1, and you can consider it absolute value because it could be a negative fraction less than 1, or greater than 1, negative 1, then what we're going to see is the fraction forcing it to widen out. Okay, so it's like multiplying by a fraction. What happens? If that fraction is something less than 1, it's going to slow it down and make it wider. Okay, so let's get to the example here. So the first thing, we have our leading coefficient 2. We have times the quantity x plus 3 times the quantity x minus 1. We'll describe how this is a quadratic function a little bit later, actually in the next section of our class. But just stick with me today and notice that there's some things that are connected using our form, our layout. And the first thing we can say is that our A is going to tell us a little bit about the picture. What does it look like? Okay, A, since A is a positive 2, we could flip back and we could say since it's positive it must open up, and the parabola, the absolute value of 2 is still 2, and that's greater than 1, so we know the multiplier in front is going to make this narrow. It's going to make the U shape kind of increase at a faster rate. It could also make it decrease at a faster rate if it were a negative 2. Okay, that's what I meant by absolute value. Second, what we're going to do now is we're going to use the idea of those x-intercepts to get 2 points on our graph. So if we take a look at where the x minus p is, and we kind of connect it to what the x plus 3 is, and we figure out the value that will make 0 inside those parentheses, the x value that you would add 3 to and still end up with 0, that'll be one of your x-intercepts. And then you can do the same thing with x minus q, because what that will do is it'll really give you 2 times a number, which would be 0, times another number, and our output anytime you multiply with 0 is 0. So your output is the x value comma 0, and that's just an x-intercept. Okay, so we're going to get 2 of these, 2 separate points. Okay? So let's say x minus p, let's say x minus p is the same as x plus 3, and we want to know what makes that 0, and x minus q is the same as x minus 1, and we want to know what makes that 0. So the first value, hopefully it's clear that it's negative 3 that would make that equation true. And then the second value should be 1. Now, as I stated, these are points on the x-axis because as an input-output relationship, they force y to be 0. So literally, I can make the ordered pair negative 3, 0, and also the ordered pair 1, 0 as a result. Sometimes I just let my kids know that these are x-intercepts so they can just plot them on the x-axis when they get them. But this is really why we're allowed to, because they do make an input-output relationship on the x-axis. So I'm going to plot negative 3, 0. I'm also going to plot 1, 0. Okay? This next step, sometimes you need to do some math to do it. Sometimes you can almost just look at the picture and figure out where is the axis of symmetry. It's got to be right in between these two intercepts. So the next step is either to average them or just kind of eyeball it up. Okay? Now if I'm just going to eyeball it, I'm looking in between these two. I'm looking in between these two points right here, and I could probably assume at negative 1 would be my axis of symmetry, and that's correct. If we want to show the math, you would say negative 3 plus a 1, all divided by 2. That's how you average two things. You divide it by 2. Will give you your axis of symmetry, which means it will be negative 1. So anytime you have the axis of symmetry, I like to draw the line in the middle so that if we do have some other points, we can reflect them. Okay, there's our line of symmetry. Also, with that line of symmetry, is that keeps us in line for finding out where our vertex has to be. And to go back to step number 1, we saw that it has to open up and it's going to be narrow. So in my mind, hopefully you'll get this too, in my mind, if it has to open up, my vertex has to be below these two intercepts, somewhere down in here. Okay, if it has to open up. If it were up here, that would make it a negative leading coefficient, meaning it would open down. And we know that A is 2. So it's got to be down here somewhere. Worst case scenario, kiddos, just plot a point down here, and that'll be a rough estimate. It won't be perfect, but if you forget what to do next, that's the best idea. Okay? So we're going to actually use the axis of symmetry like we always do. Since it's an x, we can plug it in and figure out a y value that would correlate on that vertical line. So if we plug in the negative 1 into our original function, y equals 2 times negative 1 plus 3 times negative 1 minus 1, we can get a y value for this, 2 times negative 2, which would make negative 8. This y value corresponds to the negative 1. As a result of the negative 1 that we plugged in, we had negative 8. So it's a coordinate that would represent our vertex. That's the way the axis of symmetry works. Anytime you have it, you can use it to find out the vertex where at on that vertical line. So we can plot negative 1, negative 8, and make our smooth curve. And there we have it, the parabola for an x-intercept equation, a quadratic function in x-intercept form. I hope this little video can help you. 4 steps. Again, it's like every single one of these types of equations has had 4 steps to get it done. And they're all kind of related to either some sort of intercept, the axis of symmetry, and a vertex.